lecture, The Invisible Universe, Higgs, Dark Matter, Gravitational Waves. Yes.
Oops, no. Okay. So thank you, Yang. I am super happy to be here today, and I'm trying to see how to get this to work. Okay. So it's a real pleasure to be here today with you. I will tell you, we will explore together the invisible universe, and that will go from the Higgs field that is related to the Higgs boson, to dark matter, to gravitational waves. And while preparing this talk, I realized I found on the web this talk I gave, the same series, so the Pagel series, but this was 23 years ago, almost to this day, July 24, and I was talking about Higgs physics, the origin of mass. So this was when the Higgs was not discovered yet. So, so for those of you who came back after 23 years to listen to me, welcome. I will update you now. No, I'm just joking. So let's go on. So while preparing this talk, I was thinking about the time I was watching the Flying Dutchman, that is a Wagner opera. In fact, was running the Denver Opera House last February 2024. So maybe some of you saw it. So this was in Berlin. And at that time, I was with my 5-year-old son that you will see later on, but not the 5-year-old. And so it was quite, you know, maybe quite impressive for me to go there and bring. I think there's a lot of noise going on. Sorry. Is that true? I'm trying to be good. So I was there with my son, who was 5 years old, and it was really a bit insane of me to bring him there, but he was really very excited. And we were sitting exactly here, and so we have a bird eye view of the stage. And in fact, in this presentation, do you hear my the noise or not?
Yes.
It's okay, because I keep sorry, maybe two. They are better. Good. So I hear it a lot, so it's annoying to me. Okay, so we go back. So we were there. We were sitting exactly here. We have this you know, this bird eye view of the stage. And in this presentation of the Berlin Opera House, this ship here was coming from back the stage into the public flying. It was really impressive, okay? So we were amazed by what we saw. But what we didn't see was firing our imagination much more. Okay, so today, I will bring you to look at the unseen or the invisible world and how it really makes the magic that we see every day in our world, in our everyday life and in our world, come true through this lecture. So, I will start with 3 pieces of the unseen world that are kind of connected. The first one is the invisible field of energy. So this is makes possible all what we see, and that means you and me, the stars, the galaxies, and the opera houses. And Mr. Higgs thought about this invisible invisible field 60 years ago, and it took really to build this impressive Hadron Collider that we will see later on in order to be able to prove the existence of this field of energy. Second is dark matter. Dark matter is actually what shapes the fabric of our cosmos, and in reality is what holds our own Milky Way together. As we'll show later, distorts the images of distant galaxies. And if you think about this theater analogy, it's like what we know is there, we don't have any idea of what it is exactly. It's like, you know, we know that something is holding that ship, that it's flying towards us, but we don't see exactly what it is. And then our gravitational waves. Gravitational waves are actually ripples in space-time that were predicted by Einstein's theory, but only 10 years ago we were able to actually detect them when 2 black holes merge, and I will come back to that. And in the analogy of the theory, of the theater, sorry, these gravity waves are like the music that is there on the background. If it is not strong enough, then actually we cannot see it. Only if the event is sufficiently violent, as these two black hole mergers, we are able to see. So let's start with invisible Higgs field. Okay? So the invisible Higgs field is a field of energy that permeates all of space. And in order to make you more acquainted to the idea of an invisible field, let me think about the Earth magnetic field that we all know about. Right? The Earth magnetic field is sourced by the Earth, has a direction that is determined by the Earth spinning around its own axis, okay? And it permeates the nearby space. We don't see Earth magnetic field, but we know it is there because we know that we have a compass, the needle will point towards the north. And we know that this magnetic field is there. So now I want to introduce you to the invisible Higgs field. And I hope you see it here very clearly because I put a lot of effort in making it there. So I hope you get it. So this is the Higgs field. I introduce it to you. Is sourced by itself, okay? Has no direction, and it permeates the entire universe. And how we know that it's there? Well, we know that it's there because it is mass to particles. What does it mean? It means that in our modern physics, we know that we can allow that the Higgs field turns on itself everywhere in the universe, basically instants after the Big Bang. In that process, give masses to the fundamental particles that makes you and me the shining stars in the night. It means it makes possible that we give mass to the electrons and to the up and down quarks that are the two particles that make the neutrons and the protons inside the atom. Okay, so it's very important because if the Higgs field would not have turned on, we would not be here today. Okay, so how do you know invisible Higgs is real? You should ask me, correct? Are you asking me that? Yes, good. Good question. So, well, I was here with Mr. Higgs at the Nobel Prize ceremony and with my good friend Fabiola Gianotti, the Director General of CERN. So Mr. Higgs was telling me, you know, the first time I sent a paper about the Higgs field, it was rejected because they told me that it was not important for real physics. And then he smiled and said, but it had a very beautiful math in it. And in fact, this was part of the math that was in it. And this may not tell you too much, okay? But when you look at this, so you see this musical notation, and this could not mean much either, could be undecipherable for the uninitiated. But both music and the physics that is in this math formula can reveal harmony in nature when they are interpreted correctly by a virtuoso, Mr. Higgs. Okay? So, okay, but still, you said, great, that's all good, but how you know the Higgs field is real? I didn't tell you yet. So Mr. Higgs said, well, in my second time they sent the paper there, I said, you know, if you want to see if the Higgs field is real, you need to look for the Higgs boson. So, there we went. We looked for the Higgs boson. And we looked for the Higgs boson, and we found the Higgs boson. And look what a nice day, July 4th, 2012, we found the Higgs boson. It was a big splash all around the world, and certainly brought tears into Mr. Higgs' eyes. Okay. So, half a century after the idea of Mr. Higgs, we discovered the Higgs boson, and we proved the existence of this idea at the Large Hadron Collider in Geneva, Switzerland. This is the Large Hadron Collider, and it's proton-proton collisions. We will go into that. And you know your collider is pretty big when it's quite big compared with the Geneva International Airport. Okay. So remember this. There are 40 million event collisions per second inside this accelerator. So half a century after the Higgs discovery, we have found a new type of particle that we have never seen before, and we have discovered new force in nature that makes particles like the electron acquire mass. If the electron would not have mass, the atom radius would be infinite, and chemistry and everything we know would not take place. Okay? Let me just, I need a technical difficulty here. Okay, so let me just tell you that I will just to show you what happened inside the Hadron Collider when we create the Higgs. Okay, so this is an animation. Okay, and basically we will look what happens inside our giant detectors, the cameras. Okay, and we will basically be recreating a situation that is very close to instance after the Big Bang. So let me just. No. Do that. There is now I don't want it. Okay, sorry. So here is my LHC. So it's 27 kilometers ring, 300 feet underground. Then the electrons are, protons, are injected, and they move almost at the speed of light. They cross the French-Swiss border, no passport required so far. And these are the quarks inside the proton that are wiggling. So you have one proton coming one way, the other proton coming the other way, and they meet at the big camera, which is the Atlas detector. And when they meet, boom! Okay, we made a lot of debris, a lot of particles, but among those particles, we make the Higgs particle. And why we know we made the Higgs particle? Not because we can see it right away, but what we see is what the Higgs particle turns into. And in fact, in this example, the Higgs particle has turned into 2 electrons and 2 muons, which are like the fat cousins of the electrons, because they weigh 200 times more. Okay? So we have seen this production, and in fact, we create the Higgs, and then the Higgs kind of transform in the particles we can measure in something that is called 160 yoctoseconds, that is 10 to the minus 24 seconds. Okay, so pretty fast. So these are the powerful cameras, the Atlas detector, the CMS detector. These are like onions of material, okay? And these onions of material can look at the trace of the particles, and can also stop the particles at a given place and measure their energy. So we identify the different type of particles depending on where they stop in these detectors and what the path was that they took until that time. Okay. So these are humongous detectors. This is the Atlas detector, weighs 7,000 tons. That is the same as the Eiffel Tower. And it's 4 stories high. The CMS detector weighs twice as much as the Atlas detector. And in each of these experiments, Atlas and CMS, there are about 3,000 physicists working in each of them, 40 countries around the world. So this is why particle physics is so international and so incredible, because we couldn't do this with people from all the countries working together with one goal. Okay? So, of course, we collect a lot of data, and we need to deal with that data. And so we have the worldwide LHC computing grid. I have no idea if this is a little thingy. So we see it comes from CERN somewhere here, and it goes all around the world, 4 million computers in more than 42 countries, where scientists access the LHC data and has the power to process it and to see what is going on. So this is, I think, quite amazing.
Amazing.
Oh, we agree. So we got the Higgs boson. However, we do not know how and why Higgs field turned itself on instance after the Big Bang. We know it did because we got the Higgs, okay? But we don't know what triggered it, okay? And so this is a big mystery. Large Hadron Collider will continue collecting data until 2040. So we will use this as a powerful tool to explore the Higgs miracle that I just presented to you, and the possible existence of other Higgses, because, you know, why should be only one of a kind, and maybe other particles and other forces. So what I want to say very fast here is that when we were about to start the Higgs, the LHC, sorry, in 2009. Here we were, all the physicists, very happy, going to Emerald City. And we were hoping to understand our matter, to see the Higgs boson, to maybe find new forces, or something that is supersymmetry and extra symmetry of nature, or maybe extra dimensions of space. So that looked great, and only 3 years later, we were able to see the Higgs boson. It was impressive. However, where we are today, well, the Higgs is there. We have a lot of questions, as I will tell you in a moment. We are more in this situation, okay? So where things look a little bit less clear. And of course, we have LHC, we have other experiments around the world. Here in the US, the neutrino experiment at Fermilab, for example, is a big experiment. I feel like this little girl here is thinking that there are many lookouts, and I'm trying and I'm excited to find where is the right path that, you know, as 23 years ago I was talking about the Higgs. I hope that the things I will talk to you about today will come true, hopefully even earlier than 23 years for me. So I won't go through all of these, but let me tell you that this is the list of things that we do not know from the basic modern physics in the Standard Model. There are many. Today, I will concentrate on the ones in red. I will discuss a bit the nature of dark matter, and I will tell a bit about the connection between how and why the Higgs field turned on, and maybe trying to describe why are we here rather than not, or why there is more matter than antimatter. The two things I will talk about. So, rise of the dark side, okay? Galactic and cosmological observations, I will show you that, show that there is much more matter in the universe than the matter that we can see, what we call luminous matter. You, me, the stars, everything we can see. Okay? So dark matter exists, that's for sure. We have no clue what it is made of. That's also for sure. So, there's strong evidence of dark matter from the interactions of dark matter with visible matter in our own Milky Way. And Vera Rubin, in 1970s, decided to measure what was the velocity of the stars that were far away from the center of the galaxy. For example, our Milky Way is the solar system. And Newton gravity would say that the velocity that is here, the velocity that is here with respect to the distance of the center should go down as we go farther away from the center of the galaxy. But this is not what Dr. Rubin saw. Rather, her and her team, they measured this white line here, which shows that the velocity is much larger. The problem is that this large velocity would mean these stars here will just fly away. Okay? And the answer to that puzzle is that there is additional matter that we not see that is exerting gravitational pull, so that basically it allows these stars to go at this velocity and still hold the stars together. So of course, today we have other ways to understand what is dark matter, how much I told you how much dark matter is in the universe. So one of the ways is gravitational lensing. So Einstein told us long ago that space-time is deformed by the gravitational force that comes from matter. Okay? In such way that light goes in this curved path. And so what happens is that we see that because of this gravitational lensing, that is this effect here, this is distorted the images of distant galaxies, and we see the images of distant galaxies like this, sometimes called Einstein rings, when we look at them from our telescopes. Okay? And we have today the powerful computers so that we can try to mimic what should be the amount of dark matter, the amount of matter that should be between the source and us, so that we can see these gravitational effects, gravitational lensing effects. Okay? And in fact, this is the example where matter distribution of galaxies are inferred from this type of gravitational lensing, show that they are the galaxies, the luminous matter. Then there is a lot of other, this mountain here, there's a lot of matter that is not luminous, but is what we are calling dark matter. Okay? Good. I don't want to lose you guys. If not, put your hands up. So, what do we know about dark matter? Well, I told you basically almost all what we know. Okay? So we know that it couples gravitational to us, because that's exactly what I was showing you. Okay? We know that it's the most abundant form of matter. In fact, we know that 85% of all the matter in the universe is dark matter. We, the stars, everything we see is just the other 15%. So we are ignorant about 85% of the matter in the universe. Okay? Also, we know that dark matter passes through our bodies as Earth orbits our home Milky Way. Okay? And it orbits at 200,000 kilometers per second. Okay? In fact, if you do the calculation, you can see that in our lifetime, about 1 to 3 milligrams of dark matter pass through our bodies. Okay? So, we do know that has to be something, because of the way it behaves, has to be something different from all the particles we know. We know it can be from extremely heavy to extremely light, so light that it behaves more like a wave than a particle. In fact, the only thing we know is that the difference of mass can be 10 to the 90 orders of magnitude, so 1 with 90 zeros between the lightest and the heaviest. And there is no reason to believe that the dark matter should be one type of dark matter. You know, we have many particles. We have the quarks, the electrons, and many other particles, photons. Okay? We don't know. In fact, it is possible that dark matter is part of a bigger, larger, invisible dark world with new dark forces. Okay, so it's very hard to look for what you do not know what it is. I think it's very easy to understand. So we theorists, mostly here at Aspen Center for Physics, we make educated guesses of what dark matter can be, and our brave experimental colleagues go there and develop amazing novel techniques to try to detect it. So we go all over trying to find it. Okay? So these are many ideas, okay? These are the theory ideas. These are all new symmetries. These are some extra dimensions of space. Most of these many ideas, some of them have funny names like axions or quark nuggets or WIMPs. WIMPs is weakly interactive massive particle. It was a term coined by former Aspen Center for Physics president Michael Turner. He was trying to think about what is the universe made of. And Mike laughs that I should do this. So we have detectors. So the dark matter is coming from the halo, as I told you. It's coming through us, okay? And so we are placing detectors deep underground to protect it from other interferences. And some of the detectors are humongous, like 7 tons of liquid xenon. This is here in the US in South Dakota. And this is good to look for the middle heavier dark matter. There are other ones that are based on the same technology, the semiconductor technology, very similar to what you have in your cell phones, the CCDs. Okay? And this is like in Canada. And what we try to see is we are trying to catch the dark matter collision with the detector material deep underground. And so it basically we think dark matter will come and kind of bump the material of the detector, and we will collect some signal from it. But also, we are very ambitious. So we want to make dark matter in the laboratory. We want to create dark matter. We want to create dark matter at the Large Hadron Collider. Okay. And how do we do so? Well, we create the Higgs. We hope that with these very energetic collisions, we may be able to create other particles that we have not seen yet. And these particles maybe are going to tell us that they can then go into dark matter particles that then connect with visible particles. So how does it go at LHC? The dark matter will escape the detector. We will not see the dark matter at LHC. We will create a particle that then turns into dark matter. And what we will see is some what we call a momentum imbalance. And what does it mean? You know, this is the direction of the beam. We put our momentum, our energy in this direction. Okay? And momentum needs to be conserved. Energy momentum is conserved. So if we see something here, some visible particles in the detector, and we see nothing to basically balance this momentum in this direction, transfer to the beam, this means that there is a presence of an invisible particle that has been inferred by momentum. So this could be a typical event if we were producing dark matter. So, of course, I told you, maybe there is a whole new world out there, you know, a whole new dark sector. And if there is a dark sector, how do we talk to this dark sector? So we think that we can talk to this dark sector through a portal. Okay? And this may sound very science fiction, but it's actually just math. So the portal may be a particle that interacts both with us, the visible universe, and with the dark sector where dark matter may be connected. And the portal can involve our own beloved Higgs boson. We can have new messengers. For example, we know the existence of photons. There could be dark photons that live in this dark world, and they connect to us very little, talking to our photon. The portal can be different things. So we are looking for those portals at LHC. And this is actually an event that is a candidate to dark photon. Because with one event, we cannot say anything. But this is how a dark photon event could look. Basically, what it means, we have some collision point here with a lot of particles that we see, and something invisible in between that we cannot see with our detectors because it's not talking to us. Then suddenly we see these two muons, the fat cousins of the electron, appearing, and this could be because there was some dark photon in between that connected, that went into the dark side and came back. Okay? This is, of course, these interactions are very feeble. Okay? In fact, we have defined feeble interacting particles. That's what we are looking for. And there is a lot of people working on that. It's not science fiction. We're really trying to look at that seriously. But of course, we would need trillions of collisions to have the chance to see this. And you ask, you get it. Okay? So this is but however, it's a challenge. The high Lumi LHC, that is what will start in a few years, we are going to upgrade the project. It's already underway at CERN. We will increase the intensity of the proton beams by a factor 10. It means, remember I told you we are going to have 40 million collisions per second. But within these 40 million collisions, there are a lot of protons inside this beam of protons. Okay? And when a collision occurs, before, only 20 proton-proton collisions actually occur. The rest of the protons in the beam go by. Okay? Now, with squeezing the beam and other technologies, every time that one of these collisions occur, 200 proton-proton collisions will take place. And of course, I don't need to tell you that it will be quite challenging to find out something in this environment. These are all particle tracks. Welcome to AI. Okay, so physicists at LHC have been already, of course, using AI technology. We all know that AI is very efficient to analyze complex images. We can give a cat, label it a cat, dog, label it a dog, and the big incredible achievement of AI is that it can go on itself and figure out which are the features that are better in order to distinguish between these two categories, cat and dog. Okay? So we are trying to use that to distinguish between different particles at the LHC. Here I have a disclaimer to do, please say. First of all, I don't work in AI, so I will tell you a little story about what the colleagues are doing to AI. However, I am very honored to say that I'm planning to contribute a lot to AI through my two sons. So these are my two sons. Sebastian is working in AI for physics. Julian is working in AI for neuroscience. And here you see both of them at the Wagner Park. I heard that the tooth is going to go down, or maybe already went down. I just came yesterday. But my kids have been playing there for as long as they could stand up. So, supervised learning. So this is what we did. We trained data on simulations. Simulate what we know should be there, for example, for producing a Higgs boson, or producing top quarks, that are the absolutely heaviest of all the quarks that we know. Okay? 6 quarks we know of. So we train the data, we train the data, and we tell them what it should be. And then we let AI look, we train AI network with simulations. We simulate what should the data look like. Okay? And we tell how a Higgs should look like, how a top quark should look like. And we use the AI network to actually look into the real data. Okay? And in fact, we have been very efficient in identifying the different categories, which, as you see, are much more complex than cat and dogs. Okay? That's great. And we can even simulate something that we hope to find, like supersymmetry. We can still train the data on supersymmetry. What we cannot do is train the data on something that we have not thought about. And that would be the most interesting thing to do. Okay? And in fact, you can do that with unsupervised learning. Okay? And it has been done. Now, we do a totally different thing. We are training our AI networks, our algorithms, on data without telling, as you see, I don't have the labels here, without telling what the data is, without telling how many categories or anything. The AI itself is able to put these different categories. Of course, then we will have to see what they are. The most interesting thing is they can find a category that we didn't know about, because we didn't know we were looking for that. So this is a way to find something that we have not even thought about. This is a great story. However, there is a problem. In fact, let me say, this works so well that the top quarks here were discovered in 1995, and it were rediscovered by AI recently, where we showed the data. We didn't tell anything about what top quarks are. We didn't tell anything about anything, but AI found the top quarks. Okay? It works. However, as I said, the problem for this, and the problem is the following. The problem is LHC experiments can only record a tiny fraction of collision. I have 40 million of collision events per second. I have 100 million sensors that need to read my information. And I have no way to do that. Okay? In reality, I have these triggers. I won't go into that in detail, but I'd like to come back, so that going from the moment of the data, the moment that we go to be processing and sending it to our 40 countries to look at the data, only 1 in 40,000 collision events can be safe. And the rest, we throw it away. Okay? And the biggest part that we throw away happens here, within 1 microsecond. So obviously, if you are throwing away, there's no way back. When you threw the data, you're done. Okay? So if we were unlucky because we don't have a way to know about this, okay, we threw this at level 1 trigger, 1 microsecond after, that's it, bye-bye. So what we need, if we want AI to help us here, AI has to be used in the first trigger. And this means we need fast AI. And I'm not an expert at all, but I thought it was amazing, so I decided to tell you about it. Okay. I was impressed. Maybe some of my colleagues, the experimenters, can tell me that. So this is like a GPU data center for the large language models. This is Microsoft. The problem is this is too slow, too power hungry, and we cannot use this L1 trigger. There's something that is called field programmable gate arrays, okay, AMEN, and these are reprogrammable integrated circuits, and they have been being used. So this is not a discovery that we have made, but what we have made, or my better said, Fermilab and CERN researchers have implemented these fast AI models on these reprogrammable integrated circuits so that they can decide within a microsecond if a collision event is interesting or not. Okay, we're supposed to explore uncharted territory at the LHC, and it seems that other people are thinking about it. So I'm almost okay, actually. So I told you a lot about dark matter and about how we are trying to be as smart as we can the next 15 years of LHC, this amazing machine, try to get the most out of it. And I think this is super exciting.
Okay.
Let me just go back to the question I have, that was Higgs field turn on everywhere instance of the Big Bang, but we do not know how, why it's happening. Okay? So the point is that the high Lumi LHC and other proposed colliders can give us clues about what happened at the moment the Higgs turn on. In order to give us clues about that, we need to see how the Higgs interacts with itself. This example here is a real, so every time you see these things, this is a real event that you saw before as well. This is a real event. This is a real event with two Higgses. Two Higgses that immediately decay in two bottom quarks. Two bottom quarks here, one Higgs here, one Higgs here. So we are trying to learn how the Higgs interact with itself.
Okay.
These events are much more rare than producing a Higgs boson, 1,000 times. But the question I want to ask is, can this unique event be connected to other mysteries of our universe? Of course, I've been working on this like the last 30 years, so I very much hope yes. The idea here is the mystery of our existence. That's being a bit pompous, but what it means is understanding the imbalance between matter and antimatter. Okay? So matter is made of fundamental particles, and they get their mass through the Higgs energy field. Correct. You know that. All antiparticles, all matter particles have their own antiparticles, all the same properties but opposite charge. The electron has the anti-electron that we call it positron. It has negative charge. The proton has something that we call the antiproton. And again, antimatter, first of all, was first predicted by Paul Dirac in 1928 by trying to make together be consistent Einstein's theory of general relativity and quantum mechanics. Was predicted. And 4 years later, it was first discovered in cosmic rays. We see here our positron. It also is produced when we have radioactive decay, substance that decay radioactively, they produce antimatter. Of course, it's very hard, but we can make antimatter in the lab. So, the problem is that when matter means antimatter, boom, okay? They annihilate into electromagnetic radiation. If at the beginning of the Big Bang we were in this very hot soup, okay, we think that there was the same amount of matter than antimatter, and so that would have been just so without any perturbations. Every matter and antimatter would have find each other and became radiation. So we will not be here because everything would be just radiation. Okay? So at some point, there was an imbalance, and the imbalance is very delicate, so that a part of matter and there was an imbalance. I'm sorry. Between matter and antimatter, so that a little bit of matter, meaning us, was left. Sorry. So a bit was left, and we know that about 10 billion photons per every baryon, which is the ordinary matter, is in the universe. So this was really what happened. The point is, we would like to understand what generated this very small asymmetry, 1 in 10 billion, of matter versus antimatter. Okay? So what generated? And of course, this is where my heart comes, the Higgs field be at the core of it. This moment when the Higgs turn on, the answer of why there is more matter than antimatter, and we are here rather than not. So I won't say anything about here because of time, let me remind you that antimatter is very real. Whenever you go to a positron emission tomography, what happens is they inject you antimatter, it gets into your body, finds your electrons that are the matter, and emits light. And this is what the PET scan sees. And this is the way you find if you have electron, hopefully not, a tumor or something. Antimatter is something that you use every time you go to a PET scan. But what I'm interested to know, as I told you, going back, is the Higgs at the core of all of it. Okay? And what we have learned after years of study is that if the Higgs is responsible for generating this imbalance between matter and antimatter, then the Higgs, I was telling you, it turned on instance after the Big Bang, 1/10 of a billionth second. But it has to do it in a very special way. It has to do it forming bubbles of what we call broken symmetry. It turns on in this very special way. It's a bit violent, bubbles. And also, it needs to talk differently to matter and antimatter. Okay? For these two things to happen, we know that we need to have new particles, including new Higgs-like particles. We have learned that much. That's theory that we have learned. Okay? We want to explain it. We don't know if this is the right explanation, but we want to explain it. Okay? So, of course, we are searching for such particles at the LHC, but the question is also, will we ever know if these bubbles form or did not form when the Higgs field turned on? Because that is in the past. But we can look at the past. Okay? And the answer is gravitational waves. Okay? So we have not seen gravitational waves from the bubbles yet. Okay? But, so gravity waves are really ripples in space and time. Like, instead of in an electromagnetic wave, it's a gravity wave. So we did not think that we could detect them, but 10 years ago, we were able to detect the first gravitational wave signal in 2 places in the US. Amazing detectors in an experiment called LIGO, which basically, this is 2 black holes that are merging. When they merge, these are black holes that are like 30 times the mass of the sun. They merge. When they merge, they liberate gravity waves, and the gravity waves have an energy of the order of 3 solar masses. A lot of energy. Okay? And I would like to, I'm almost at the end here, but this is the real effect. Hope you see it. Did you like it? So this is a real thing that occurred September 18, 2025, when these 2 black holes merged. Okay. The same as you tune the radio to a frequency, and then in your loudspeakers it comes the music that you love. But here is you tune the gravitational waves to a frequency, and you hear the music that you love. It's of course much easier to tell the story like that. Sorry, I didn't want to. So, this is the end of the story. So what I told you is we see gravitational waves that are coming today, and when I mean today, it's like billion of years ago, but basically from a universe that it is what it is today. What we want now is to see, know that these bubbles, because we have a study, when the bubbles collide and expand, they also make gravitational waves. There are different frequencies of gravitational waves. We have not yet been able to detect. If we would detect those gravitational waves, we would be getting information of the time where the Higgs turn on. We will, for the first time, have a glimpse into the far, far past. So I think that's amazing. If you want to learn more about all the things I told you, the National Academy, this is just, it's been presented, and is we see the future for the next 40 years and where we are. And I was very lucky to be part of this effort. So this is a report that just came out. And last but not least, I'm sorry to all of those who may be here of my friends and I didn't put them. But of course, all what I told you, all what makes me who I am today is thanks to my many amazing collaborators. And many of them are coming here regularly to Aspen. These are my students. So the students usually don't come here, but now they are most of them postdocs, so I hope they are coming soon. But there is an amazing group of people, many of them here, including my husband Carlos. And so, last thing I want to say, this is what Aspen also means to me. It's a place where my family has flourished. So this is Sebastian, guy who's doing AI for physics, for strong lensing. When he was 6 months old, that was the first time he came here. This is Sebastian and Julian. Julian also came 6 months old. In fact, I was desperate to have help, and Angie there, who is there, was the one that helped me the first time, because I was coming with a 6-month-old and a 6-year-old to an Aspen conference, and no daycare. So, and she saved me from that moment on. So it's my angel. So this is me with the kids trying to, this was the time I was pushing them to go up. Now they push me to go up. The first time I went to a 14er was when Sebastian was 13 years old. I said, Mommy, I'm going. I said, no, you can go alone. So there was my first 14. So this is of course places you know. So they keep coming. You see, they are kind of older now. And we are even adding my future daughter-in-law and a good friend here, Howie. And so these are just 4 pictures. I have so many, I didn't know how to present it. But it's very important for me. I wanted to share this little piece with you. So thank you. Thank you very much. So there's question there. Yes, please.
2 questions. The first is, why do you describe the Higgs boson, the Higgs field turning on as opposed to always existing?
Okay, that's a great question.
Regarding the rotational speed of the outer suns and in galaxies, could that not be explained by the presence of more or larger black holes sprinkled throughout the galaxy, such that the distance from the mass is shorter?
Yeah. So the first question, okay, is a bit of a jargon to say turns on, okay, but you saw this potential that is this. Sorry?
Can you repeat the question?
Oh, I'm sorry. The point is, first question was why we speak about the Higgs turning on rather than being the Higgs field turning on rather than being there all the time. The Higgs field is there all the time. But if you saw this equation and this Mexican hat type of potential, we call it, the energy of the lower energy state, or the energy of the vacuum, change. And that's what we call it turning on. The Higgs field was always there, but the parameters of this Higgs potential that I show you change in time, in temperature, so that it went from one preferred vacuum state to another preferred vacuum state, and went from a vacuum state where this value was 0 to a vacuum state where the value was not 0. Okay? So it's the same when I say bubbles. Inside the bubble, the Higgs is a minimum energy value is not 0, and outside it is 0. So that's the idea of turning on. And in this process of turning on, and this is of course a course in particle physics, is that the Higgs give mass to the particles that we know that need to give mass. That's the first question. The Higgs field is always there. Turns on means change the energy level. The value of the minimal energy vacuum. The second question was, can we explain other ways, basically, the fact that the velocity of the stars that are far away from the center of the galaxy are too fast. Okay? And the question was, why not other black holes? Well, we are taking into account everything that is visible matter. When we take into account everything that is visible matter, the difference, and of course, this could be one example, because then you have the sample of the gravitational lensing, which is even much more robust, okay, because we see this deformation. So there are many possibilities that people have thought about to solutions, maybe have to do with changing the way gravity behaves and so on, itself, more radical. But there's no single answer besides dark matter that could fit. I only show you two signals of dark matter, could fit all the measurements we have of the gravitational interactions. She first. Oh.
Should I wait for the mic or just go?
Maybe. That's great.
Thank you. I've noticed from listening to about 50 brilliant physicists talk about their work that there seems to be two kinds of obsession. One is this
Only two?
beautiful obsessions. One, like yours, seems to be really concerned with sort of how did this all happen? How did we get here? Ultimately, what is the interface between physics and sort of ultimate, right? Did it all come about? The other is people really attracted to extending formulas and applying, manipulating the matter in this world. And so I'm curious.
The matter or the
matter? Like using these formulas to make things happen in the world. I'm just curious, like, when does this fork in the road happen? Is it when you're a teenager? Is it when you're first a physicist? When do you become one of these kind of physicists or the other in terms of what motivates you?
I think that what motivates me to think about physics in general, maybe not to its roads can even be divided in more directions. Okay?
Yeah.
But for me, what motivated me to think about going into physics was really curiosity, like plain human curiosity. And in full disclosure, was very excited about becoming a ballerina. So, but my mother didn't, I entered even the school, my mother didn't let me go there because it was Argentina, repression time, not good. She was scared. So I'm here today because my mother was too careful. But I was passionate about that. But I'm so thankful that I follow my heart there, and I hope I transmitted a little bit of that today. I of course, we are a family of physicists and a neuroscientist, so okay. But I think it's just the fact that we have the power to go and look into math and understand how the world works. And so I think that's what, it's just curiosity and the passion to explore. I guess that's the way I would describe it. Yes, please.
We've been to many lectures. And I keep hearing antimatter and dark matter.
Good.
And I would like to know, is there a difference between the two?
Yes.
And I'm getting the impression, I'm not a scientist, I'm a musician. But I'm getting the feeling that it is the dark matter that's holding us all together,
Yes.
the universe together. Why wouldn't it have its own gravitational?
It does. So this is a very good question, and honestly, it's something that happens so often because one goes fast and so on, and these are two different problems. Okay, for me, of course, the first problem. Let me just go to the one that maybe is maybe go to the one that I want to start about. Okay. So there is this idea that as I said, it was found that to solve the equations of math and the laws of physics means based on theory of general relativity and quantum mechanics, Dirac had to propose the fact that there were two types of particles, both with positive energy but with different charges. This is just electric charges, okay? And that's what it means, matter and antimatter. Okay? Matter and antimatter means that the electron has negative charge, the positron has positive charge. Other than that, it has all the same capabilities, the same properties, and that's why when they get together, they cancel each other, so to say, and they create radiation. So these are both, however, what we call matter and antimatter are both luminous matter. Luminous matter. Are both what make 15% of everything, of all the matter in the universe. That's a bit. The problem is we don't know how this imbalance occur, because of all what we know, we should not be here. So that's a question that is interesting to answer, you know, how come that we are here. The other question is dark matter. Dark matter actually has a very strong gravitational pull. Okay? So the dark matter feels gravity, and that's exactly what we need to postulate existence of dark matter, so that we can add more gravitational pull, so to say, that these stars that are going so fast are not flying away. These are two different things, but dark matter is 85% the matter in the universe. We don't know what it is. Antimatter is part of the 15%. We do know what it is, but we just don't know how that imbalance happens.
So maybe we have one last quick question. Yeah.
Okay, I see three. Well, the last three will be fast. And I think I'm going out of whatever I'm going, but go ahead.
Hi. So I asked a question last week that I got some laughs. I think Albert Einstein took a wrong turn with the abolishment of ether. And one of the reasons has to do with so much of what's in your lecture. Dark matter is exactly what ether was understood to be. So why does not the observation of dark matter demonstrate that ether exists?
This is a very difficult question. I'm being politically correct. It's different. It's different. Ether has, I don't even know exactly in my mind what were all the ideas of ether, but the ideas of dark matter are just matter as we are, only that we don't know if it has electric charge. We don't know if it interacts with us in any other way than through the gravitational interaction. Ether was just, if you want to say it in the best way, we don't know how to explain something. What we do, theories do, we try to make it like what it could be if we could explain. So that's what we put into ether. And maybe some little part of whatever you are thinking would be some possibility, but in reality, it's not the right explanation. So, 1, 2, and I think is that okay?
You talk about bubbles. Bubbles, I suppose that's an analogy. So bubbles are manifolds in the 3 dimensions. So is that why you call them bubbles? Are they some lower dimensional manifold embedded in a higher dimension, or why do you use the term bubble?
So bubbles means much simpler. It's much simpler, okay? Suppose that you are thinking about two phases, like you have water, it starts to boil, okay? So then the bubbles of that water that boils escape. So there are two phases of water. Here, bubbles are two phases of the Higgs field. So when we go, these bubbles are what we call a phase transition, and are basically, that's the way we are thinking. So they are just bubbles in the sense that in the field space, okay, the whole universe is first place where the Higgs has no vacuum expectation value, let me say, so, or has a vacuum energy that is 0. And then they start to appear, bubbles in my space where this Higgs field has a different value. And finally, it expands, and the whole universe is where we are today, where the Higgs has transitioned to be a different vacuum state. Okay, but if you want, we can talk more if you like to. Oh.
It's a little bit related to my question. In your colleagues' research, do you believe that the actual known Higgs boson interacting with dark matter, or is it the Higgs type of particle that you're still searching for that's interacting with dark matter?
We don't know. I mean, there are many theories. In some theories, the Higgs has some what we call an invisible decay. So the Higgs can be, when invisible means we don't see it at the LHC. And okay, yes, so That's the point. So basically, Higgs could be transforming into dark matter particles in some theories. In some other theories, Higgs could be talking to, we call it dark Higgs. That dark Higgs could then talk to dark matter. So it's very dependent. The Higgs, as I said, the Higgs could be the portal to the dark sector. So we don't know, unfortunately. We have theories where both things happen. Okay, so that's where we are. So we are exploring. We are exploring. We have plenty of ideas, that you can believe me.
Okay, let's
thank
thank
you.
Dr.